CDs for this conference will be available after 11 o'clock. For politeness purpose, could you, with loud cell phones, set it on vibrate or just turn it off? If you're so important that they need to contact you, you may not be promotable. Let them really worry. I'd like to introduce Gen 3 HoneyNet's subject today, the birth of Rue, with speakers Alan Harper and Ed Balas. Thank you.
Thank you. Thanks for coming this morning. It's an honor to be before you, and we appreciate the opportunity to talk to you. My name is Alan Harper. I am the lead developer for the Rue technology that we come to talk to you about today, and I'm also a co-author of Gray Hat Hacking, available out on the table. Please go by and at least take a look at it. I'd like to also introduce Ed Balas. He's a researcher at Indiana University, and he's the lead author of the CBEC project and also took up lead on the data capture and data analysis portions of the Rue, and he'll be presenting the second portion of the brief. Here's the agenda we're going to go through today. I want to start out just with talking about the HoneyNet project a little bit. We're a bunch of volunteers. We volunteer our time. We use open source tools and methods, and we deploy networks all around the world that are designed to be hacked. Everything we capture is in the wild, and hopefully, we're trying to be on the bleeding edge and catch new stuff. We have no agenda, no employees, and no product to sell, and our goals are laid out right here. We just hope to increase awareness in the security field. Once you get that awareness, we hope to provide you with some information. I know myself, when I got into this field, the data that was provided by the early Gen 1 and Gen 2 HoneyNets was invaluable for me, so we hope to provide that type of information. And then also research for organizations so that they can use the capabilities to learn more on their own about their own networks. I also want to tell you a little bit about the HoneyNet Research Alliance. It was started in 2002, and it's a forum for exchanging information and ideas. It's international in nature. If you go to this URL right here, you can find out a whole lot more information about it. And these are the present members of the Alliance. If you're a member of an organization or a school or something like that, and you'd like to participate, I encourage you to go to this URL and find out more information. Okay, I'm going to do a brief overview of the history of HoneyNets. This is the formal definition laid out a couple years ago by the HoneyNet project. But essentially what we're talking about is an information gathering system that's built to be compromised while being watched. So we put systems out, we want them to be hacked, and all the while, hopefully, we're watching and learning. There's no production value in these systems. Anything that's going to or from the honeypot is likely a probe or an attack, so therefore they have generally very low false positive rates. So you can be pretty much rest assured that if you get activity to your honeypot, it's probably a bad guy. The primary value to most organizations is information, and by that I mean two things. It provides early indication and warning of attack. You might have other sensors in your network, but they're probably bogged down with false positives. So you can put some honeypots out there and get that low false positive rate and get some early indication warning. Also provide you, we hope, some network defense intelligence. And by that I mean, if you learn something about the attacker and their methods, then you can look for those methods elsewhere in your network and use that intelligence. In honeypot technology, there are generally two types. We have low interaction and high interaction. Low interaction is basically faking it. We emulate services with Perl scripts or other methods. And generally, yes, we will accept a three-way handshake, TCP handshake. It might provide back a banner of some sort or something like that, but that's pretty much it. There are some more advanced ones. If you're interested in this, I encourage you to look into the HoneyD project. You can script up back-end scripts and provide full web servers and everything. But again, you're emulating it, you're faking it. On the one issue here is that it's very low risk to deploy these because you're faking it. They have no access really to the underlying operating system. So therefore, there's not a lot of supervision required, very low maintenance. On the other hand, you're not going to get a lot of valuable information out of this. You're going to get a lot of worms and stuff like that. On the other end of the spectrum, we have high interaction. On the extreme end of that is a real system. You could put a real system out with a real operating system, probably unpatched and allow it to be compromised. But as you can imagine, this requires a lot of supervision and a lot of maintenance. And but you're much more apt to get valuable information with this system. By the way, most often we use VMware. Many of us that deploys technology use VMware on the high interaction side just because we can reset it and we can save it and much easier to maintain. Quick review of Gen 2 HoneyNets. Again, I encourage you to go to this URL. It's provided in your slides, in your book, and get more information. In particular, I want to point out this Know Your Enemy series of papers. We call it KYE, and a very valuable resource for those of you that are particularly new to the field and want to get up to speed on what the Black Hats are doing out there. Essentially, a HoneyNet, quite simply put, is a collection of honeypots in its simplest terms. Most often, they're high interaction honeypots. Back in 2001, the Gen 2 architecture was set forth by the HoneyNet project. Essentially, a Gen 2 HoneyNet is a HoneyNet that provides at least two services: data control and data capture. By data control, I mean that you want to limit the amount of damage that can be done from one of your compromised honeypots. And so as you deploy this technology, one of the worst things that can happen to you is that somebody take over your honeypots and then use them against you back into your organization or against somebody else. And then you have some liability issue there perhaps. So we put some data control measures in place. First of all, it's the technology provided a layer 2 bridge so that the attacker could not see that you're on the network. Next, we use IP tables to do some packet limiting. There's some rate limiting and so forth that we do in there. We can also set up rules, of course, to keep them from going certain directions. And then most notably, big advance in Gen 2 was the snort inline, where we take packets up to the application layer and say something and scrub those packets. You can once you get them up to the application layer, you can either drop them or you can actually change them and sterilize the packet and let it go on its way. When we talk about data capture, what we're talking about right here, if you can look at the screen, I'll move the mouse, I think. Maybe not. So as we have our Honeywall right here, the Honeywall is the device that's going to provide this data control and data capture. And that's located right here. What we want to do is we want to capture data on this device, and we will put it all in one place so that the analysts can come get a look at it. And the things that we captured on Gen 2 are snort, IP tables, logs, and CBEC. For those of you that are new to this, just let me say a little bit about CBEC. CBEC was designed to address one issue. What happens if an attacker comes from the internet, comes down through your honeypot or HoneyNet infrastructure into your honeypots, and then they go encrypted? At that point, you're blind at this network appliance level right here, and you can no longer, any of your sniffing devices are blind at that point. So what happens then? So Ed over here developed CBEC many years ago, and it's basically a keylogger that sits on your honeypots down here and allows you to covertly siphon or get the keystrokes off of the honeypots, and they go back up and they get caught up here on the honey wall so that you can come in and collect those keystrokes. So no matter what encryption that they're using, you still have their keystrokes. There's some limitations to it, but that's essentially what it does. Ed, anything else you want to add to that?
Yeah, it basically, when I first started doing HoneyNets, I remember my first big hack. What ended up happening, this is sort of an anecdotal story, was, I don't know if any of you have ever been hacked by Romanians, but that was my first catch. And what ended up happening was they came in, something they did caused Snort to basically vomit, roll over, and die. And they turned around and immediately they installed SSH and they started outbound, basically DDoSing some folks. Now, luckily, I had a FreeBSD firewall sitting in front that was doing rate limiting, so that was kind of a success. But everything else pretty much was a failure. And I started looking at the situation and sort of, I felt like I got taken for a ride. So I got kind of frustrated and started looking at, okay, how can we make sure this doesn't happen in the future? And so what we did, we basically developed a platform similar to a rootkit that sits inside the kernel and monitors various things. And the first thing we monitored, of course, was keystrokes. And later we'll go into what we expanded it into.
Yes. Now, all the Gen 2 technology was encompassed in this product called Eeyore, and that's been available for several years, and you could download that. Many of you probably have experience using Eeyore. It was based on Red Hat 7.2. Okay, now I'm going to get into what we really came to talk about, which is Gen 3 HoneyNets. We developed this new honey wall, and we call it the Roo, in keeping with the Disney theme. So now we have Eeyore and Roo, and I'm sure someday we'll have Tigger and Pooh and Kanga and the rest of the group. We're working on that. So you can download this right now. It's available at this URL. The public release was back in May, and we have a real good first release. We actually have a beta that we're working on right now for the next release, and at the end of this presentation I'll give you an email address that you can get on that beta mailing list and get access to the very latest bleeding edge technology. But I encourage you to go out and download this. These are improvements that we made over with Roo over Eeyore. I'll be talking about these in the next slides. Okay, the installation of Roo. So anybody in here that has used Eeyore realizes that Eeyore was a bootable ISO, and it ran off of the CD-ROM. So you had to leave it in the machine at all times. And of course there's performance limitations there. One key change that we made with Roo is we made it Fedora Core 3 based. So the entire CD, the next thing that we did was we took the Fedora Core 3 install disk and we remastered them. So we got everything that we needed on one CD. And we built a custom ks.cfg file that does an automatic install for you. So our idea is that we wanted a bootable ISO too, but this bootable ISO is to install. So in 3 to 5 minutes, depending on your hardware, totally hands off, from start to finish, you put the CD in, you go ahead and boot it, go get a Coke, and you come back and you have a fully running, functioning Honeywell, a Roo, ready to be logged in. We run a lockdown script on the first boot. It was based on these elements here. And also you have an option to do auto config on the first boot, and I'll talk more about that in a minute. This is what the Roo looks like when you first bring it up. Notice the big warning down here. It says that continuing will overwrite your existing hard drive. We initially had this screen up and it would stay up for 60 seconds. It would automatically continue because we had these dreams of a headless install. But we decided to go ahead and put a pause in here, so you do actually have to hit return. So we want you to realize that once you hit return, you're past the point of no return. We've had a couple complaints with that. You should not test this on a real production system. This should be a system that you intend to be a HoneyNet, and you're going to lose whatever was on that hard drive. So first thing it does, goes out and formats the hard drive, and then it copies all the files in. But the key here is that we have our own ks.cfg, so you don't have to worry about anything. If you're familiar with the Fedora install, you normally have to do minimal or whatever. We took all that away from you, so you don't have to worry about it. You just put it in, and seriously, go get a cup of coffee, and come back in 3 to 5 minutes, and you're staring at a login prompt. The system will reboot when it's done. When you log in, the first thing you'll see is a configuration menu. This will be familiar for those of you that used Eeyore. This is a bash dialog script that runs a menu system for us, and the first thing you want to do is go to menu item 4, which is the Honeywell configuration. Menu item 4 looks like this. We have 3 ways that you can configure your Roo. You can put a floppy in and pull a honeywell.com file off of it, or you can select number 2, which is the default, what we like to call factory settings. So the Roo comes with a default honeywell.conf on board, and we use it for testing. It just has some 10.0.0 space settings in it, and I encourage you to use that for testing. It's a quick way to get the Roo up and demonstrate it, and it happens to be the exact settings we're going to use today. You can also walk through an interview process, which again, if you use Eeyore, you're familiar with that. It asks you a series of questions and it helps you configure your Roo. Okay, now I'm going to move to the operation of Roo, the improvements that we've made. We added a command line tool. It's called HWCTL. It's very well documented. If you do HWCTL-H, it'll give you all the command line options, and there's way too many of them to mention here. And you can pretty much do anything with the Roo. Start, stop things. You can set configuration variables, all of that. We improved the old console SSH access dialog menu that I just showed you. We added some items, moved some things around, cleared up some things, reduced some things that were redundant. So I think you'll like that. But the thing that we're really here to talk about is our shiny new web interface. We call it Walleye, and Ed was a big part of that. It's SSL based. It uses role-based authentication, so you can have user-level privilege and administrator privilege on your root. That was very important to us. And then also you can do total system management from the web interface. So by that I mean you can check the status of your root, you can clear logs, and you can also configure your root totally from the web interface, of course, after you get it up. And then most importantly, you can do data analysis. This is what it looks like when you go to log in. Of course, you put in a username and password. The first time you log in, it's going to force you to change the password. The default password is honey, and this is all in the documentation. And it's going to force you to change the password, and it's going to use the best practices. You have to use at least 80 characters, one upper, one lower, one special, all of that. And if you screw up, it'll remind you, it'll pop up and remind you. Once you log in, you actually get this lower screen down here. I just was trying to save slides. And you notice over here you have a system admin tab and you have a data analysis tab, and Ed will be going through those in a minute. Maintainability of the root. One big change that we made was we made everything on the root RPM based. Now if you used Eeyore before, you realize once you got it and installed it, you were stuck. If a vulnerability came out on SSH the next week, you were stuck. And until the honeynet.org guys updated root, you were stuck. So now it's very important to us to allow you to update and maintain your own root. So the whole thing works off of Yum repositories. We primarily point to 3 of them right now: Fedora, the DAG, and the honeynet.org. We set up our own repository for the RPMs that we made. So everything on the system is RPM based. Customization of the root. Again, if you used Eeyore, you realize that it's very hard to customize. You basically had to recompile the whole thing. But this was very important to us to make it easy for you. So there are 3 levels. The first one you pretty much had available to you with Eeyore 2. You could do standalone customization. By that I mean on the first boot, it's going to check for the presence of a floppy. If a floppy is in a machine, then it's going to check for the presence of a honeywell.conf file and SSH keys or SSH keys. So the idea is that you could preload these floppies, put them in machines alongside with your bootable ISO, and it will totally configure itself, and then you can ship the thing off and you can connect directly to it with SSH keys immediately on the first login. It's pretty important to us. Also, once you get it up, you can do the natural dialog menu customization, or you can manually edit the honeywell.conf. You're free to do that. It's pretty well documented and commented, and then you can load it back in with HWCTL tool or reboot. The next one is pretty important to us too, factory mode customization. This allows you, everybody in this room, to download the ISO, and there's an unpack script that's on board the ISO. You just have to mount the ISO and go into a customization folder, pull this script out, and you run the unpack script with this syntax right here. It'll unpack the whole ISO for you on your hard drive, and you have to have a Fedora Core 3 system to do this because it uses some Python and stuff that needs to be there. And then once you have it unpacked, you're free to go in there and make all the changes that you want. You can change the password, you can add web pages, you can do whatever you want. And then you run this script or run the command make ISO from inside that unpacked directory. We have a make file in there. It'll automatically roll it back up, and in about 20 seconds or so, you'll have another ISO that you're free to email out or whatever, email a link out or burn to a CD and distribute internal to your organization. So truly, if you have something you want to change, it takes like 30, 60 seconds to change it and roll a new ISO. And then we use Foundry mode customization, where all of the developers are linked via CVS and it synchronizes and so forth. There's online documentation of the root, very well documented. There's hundreds of pages of stuff out there, and even screenshots and stuff like that. So again, go to this link. This is something we're pretty proud of. We did improve the data control of Eeyore by implementing 2 features. We call it Roach Motel mode and Fenceless mode. Roach Motel mode basically, as it implies, allows hackers to attack in, but they can't attack out. So quite simply, the IP tables won't let them do that. And of course, we're layer 2 bridge, so they won't know why they can't do it, but they just can't do it. So you might have a use for that. Also, fenceless mode allows you to identify a set of systems that you absolutely don't want the attackers to attack from your honeypots and hit. So perhaps these might be sensitive systems inside of your organization. So you can put a fence around those IPs was our idea. And that way the attackers can go back out, but they can't touch those systems. Okay, now we're going to move to the data capture and data analysis portion of the brief.
Okay, so what I'm going to do first is talk about data capture and then data analysis. And my general approach for doing that is because if we don't get the data in the right format, data analysis is just a nightmare. And what I'm going to do now is talk about sort of the review of what we had in EOR, in the Gen 2 technology, which was, compared to the prior, was a great improvement. Because we defined a set of standards, or started to, we had three things we basically said, okay, here's what we need to collect for you to be Gen 2. And so we needed firewall logs. In the Gen 2 world, these basically acted as crude Argus records or flow records, and I'll get into that later. We had IDS alerts for obvious reasons. We had raw PCAP data so you could see what was going on at the packet level. And those were our three data sources primarily. And this was great because, you know, when Al and I needed to share data or something like that, we knew what to expect because, well, you know, we were all collecting the same type of data. But there were some limits there, of course. And these limits, the upshot of all these limits I'll go into briefly is our analysis abilities were impeded and also error prone. And this was caused primarily by the fact that we didn't really have, a defined data format. We said what type of data we had to collect, but we didn't say what format it had to be in. For instance, you know, okay, yeah, we're going to store IDS logs. Well, are we going to store them in unified format, or are we going to store them in sort of the default format? So we had no comprehensive data format. That's not a good thing. The other thing related to that is because we had no defined format, we had no way of going from one type of data to another. For instance, if I had IDS data, could I then go to P0F data and try to combine those two to say, is this a false positive? Well, there's no real way to do that in Gen 2. Additionally, we didn't have an API for programmers who wanted to write tools to get to that data. So if we moved the data in the directory, someone would say, hey, my tool just broke, where'd the data go? That's not really good, right? And so the end result was we kind of had a stovepipe effect. And I imagine some in this community probably are all out stovepipe effect, right? We've got a set of data here, set of data here. Each has its independent tool for examining, but the tools don't talk to each other, and so we can't get a good big picture. And this is my, you know, my feeble attempt at becoming a manager here and showing these cheesy graphics. But really what the problem to me, in my mind, is illustrated here, which is we've got a variety of data sources coming in. And because the system doesn't combine them for us, the analyst has to basically create a composite view of an intrusion sequence in their head. Okay? And yeah, okay, that's better than nothing to start. But again, when I need to talk to Alan and say, hey, I'm seeing this, how do I share that composite knowledge I have with Alan? There's no way to do it. I can't take it outside of my head and export it to him very easily. So I have to use things like words. You know, that's slow. So what do we want to do? Where do we want to be? And so really our whole goal with the Gen 3 technology was we want to shift this mundane screening and coalescing of the data. We want to shift that burden away from the human and put it on the computer. You know, computers are sitting there idle, you know, 1% CPU, probably on average or whatever, right? Let's put those things to work, make them do all the work for us. And because we're a volunteer organization, you know, our time is completely taken up. So anything we can do to remove the amount of work we have to do is great, because then the humans can focus on the things they're good at, you know, advanced pattern recognition and all that stuff, right? So to kind of get to there, what we wanted to do is come up with a comprehensive data model, okay? And based on that data model, come up with an ability to take all these data sources, fuse them together, and put them in the model. And then, of course, provide an API for programmatic data retrieval. So we started looking at this, and you know, we saw, well, the problem is we've got two competing needs. At the one hand, we want to be able to come up with this high-level sort of intrusion sequence perspective that allows us to quickly see what an intruder does when they get into the system. This allows us to see incident scope and all this other great stuff. But conversely, once we see what they do, we also need the ability to be able to drill down to the lowest level. We need to get down to the packet. So we need to keep sort of two types of data. And so what we decided to do is, well, we're not going to be able to keep it in one data model, so we'll sort of keep two and try to relate the two data models. So we've got this, what we call the fast path data model, which is a relational database that has this unified model in it. We've got a slow path data set up where we keep the low level, the canonical data, the PCAP data, in a repository. And then later we'll show how we actually keep a link between the two. So the model itself that we use for the fast path is, here's sort of a crude example, but the key thing here is we sort of really gravitate towards 4 abstractions. We have this notion of a host, obviously, on the network. Within the host, and this is because, again, we're using CBEC and we can get to this data, we have this notion of a process. Third, we've got the notion of a network flow. I talked about earlier in Gen 2, we used firewall logs to basically do connection tracking, so we could see anytime there's an inbound or outbound flow. Well, what we decided to do is go to something a little more nuanced, and so we went to basically Argus, which provides us a bidirectional flow accounting capability. Fourth, we have the notion of a file, which resides in a system and is associated with a process. What we wanted to start doing there was to sort of augment traditional disk forensics. We wanted to be able to see whenever a process touched a certain file, and I'll get into why that's kind of cool later. The key really with all this is, for any of these 4 abstractions, we want to be able to link between them. That's where all the, that's where the good stuff comes into play. And ideally, those links should be identified by the system, and all the work of putting it in the model needs to be done automatically, and I can sit back and drink my Coke. So when we look at the slow path data model, that's a pretty, it's a pretty simple deal. What we have is basically the raw data being stored somewhere, and in this case, it's PCAP. Our goals with it are to provide a degree of location and storage format independence. That's going to be important for down the road when we have a distributed capability, which we'll get into. And the other thing we really need is this ability to go from this high, this high-level detail data to the low-level data. And we need to basically, we'll go into that later, how we can do that. So to implement, basically, we've got 3 components in the data. These are the data capture side. Actually, one of them here is data analysis. But we've got the 2 components in question here are HFlowD, which does the data aggregation, the modeling, and the fast path stuff. And then we've got the PCAP API, which is the slow path, the low-level stuff. But in order to make HFlowD exist and make it happen, we had to enhance our host data capture capability in order to identify all these relationships between processes, flows, and files. And so, of course, our host data capture capability is CBEC. So we had to augment it. And so we had a new generation of CBEC come about. I'm not going to go into too much detail about CBEC version 3, although there is a whole slew of improvements in there along the routes of the ability to actually exfiltrate data out of there at a higher rate than the original version. But the thing that's important here is we added 3 new capabilities, basically by trojaning additional system calls. So the first call we went after was the open call, and we needed to do that to get the file activity. Then we went after all the fork calls, clone, et cetera, so that we could actually recreate the process tree. And the process tree is going to be key to identifying incident scope. And then lastly, we had to get the socket calls. And this allowed us to basically associate a process with a specific flow in the network. And this allows for basically us to relate inbound flow to outbound flow. And we'll show that later. So HFlowD is it's actually not all that sexy. It's a pretty simple Perl daemon. It's a single-threaded app that does non-blocking reads on a series of inputs. And its whole purpose in life is to automate the data fusion. So we take, of course, this Argus data, the snort IDS data, snort inline IDS data as well. The CBEC socket records we take from the CBEC daemon, and we also have, we query P0F to get the OS fingerprints. Using that data, we combine it all, and we put it in a normalized relational database for Walleye to examine. On the right here, we can see sort of a schematic of how this actually looks in the architecture. Again, you see that we have the four feeders going into the Fusion tool, which then dumps into the database. At the same time we're doing that, and we do this continually, on the right we have a traffic recorder recording, using lab PCAP as well, that dumps into a PCAP archive. I should note that all the tools, including CBEC, the daemon, the receiver, these are all passive tools. We don't have any network connections to the hosts. This is all sort of passive sniffing. Okay, so what does this really give us? We've got all this great data in a model. Why does anybody care about this? Well, there's a couple things we can do that really make our lives easier. I'll list just a few of them. First, for a given flow, we can identify the initiating host's OS fingerprint. This helps us understand a certain amount about the adversary that's coming in at us. Second, we can identify quickly all the IDS events related to a flow. This is really huge. You know, in Gen 2, when we're doing data analysis, we may have a whole series of, you know, like an nmap or whatever, or pings, and you'd have thousands of IDS alerts, and there's no way to collapse them. Now what we can do is we can organize them around the flow, and sort of we can say, okay, this flow is not interesting, and I can ignore it, and then immediately, of course, you ignore all of the related IDS events. And then third, we can see which processes on the honeypot, and files for that matter, are related to a specific flow. So we get an inbound connection into a honeypot, we can see the process tree that was caused by the inbound flow, and we can then also see all the files that were touched as a result of that inbound flow. So again, we can very quickly see which parts of the disk we might need to examine for side effects. So the other thing this does is, you know, again, we got this flow data, and this is where we can then basically, once we find an interesting flow, we can then dive back down into the low-level data. This high-level data acts as sort of, it gives us the central theme of an intrusion sequence. Once we quickly identify what we're interested in, we can then dive into the, you know, if we need to do some packet tiering, we can dive into the packets and go from there. So the slow path data, we have a PCAP API to get to that. I'm not going to go into too much detail, except for basically, it takes as inputs either a Berkeley packet filter plus a time range, or a flow identifier from HFlow. And using either one of those inputs, what it gives you is a dynamically generated PCAP file that contains just the packets you're asking for. And so the reason we did this is that we needed to provide a level of abstraction. You know, the data analysis programmers don't need to be looking at what's on file. They need to be saying, I need this data, I don't care where it's at. Because in the future, the data may not be local, it may be some site, you know, remote, and they don't need to know where it is. So we talked about how we go about gathering data and how we sort of put it into a model. What we want to do now is talk about what we can do with it. And so we created Walleye. Alan talked about that a little bit. The whole idea really with it originally was, from the data analysis perspective, is provide a big picture intrusion sequence comprehension. We didn't want to create a monolithic solution. So again, all of our analysis is, we saw those 4 things earlier. We organize our analysis around it. Flows, processes, and we try to navigate between the two. So some things we can do basically is for an outbound connection from the honeypot, we can then backtrack and say, what was the inbound connection? So we have a 0-day launched against us. We can, you know, when we miss it, the IDS misses it, we can then backtrack from the outbound, which shouldn't be happening on a honeypot, to find the inbound, and then look for signatures in the flow. A variety of other things here. We're getting a little tight on time. So here's sort of what, we're going to do a live demo here very shortly, but what I do is just show you a couple snapshots. This is basically the overall view. You see you have a summary of online sensors, some activity. You click on something in there, and you get down to the flow view. We'll show you that in detail here shortly. The other thing we'll get into is when you then jump from an interesting flow to a process, you get into the process tree view, which is all navigable. It's an image map. We'll show that as well. And then from there, you can say, show me the details on a specific process, and now you're down into the keystroke logs. So this is a quick thing I wanted to show. Can anybody tell me what's interesting about this process tree? And what I'll show you is the yellow boxes are root processes, the cyan boxes are non-root, and the red ones are IDS events that are related between them. Yeah, sort of. This was sort of done by accident. I was doing a test in my network, and I was too lazy to go outside my network to actually attack between the 2 hosts. And so I basically both hosts were running CBEC, and I broke into one from the other. And I didn't even really mean to do this as far as the programming, but it actually picked it up. So the system actually has some interesting capabilities taken to a larger context. There are some limits, of course. HFlowD is primarily the one. We added a lot of complexity, and if it fails, you know, okay, we lose our Gen 3 capability. Oh, are we screwed? Well, maybe. When HFlowD dies, basically we have to fall over to a lower tech backup plan, which includes essentially the traditional Gen 2 data analysis techniques. And The other thing that kind of sucks is we don't have this ability yet to go to do non-real-time data fusion. So if HFlowD dies, we can't yet go back to the Gen 2 data and recreate the Gen 3 model. We'll do that in the future. So what Alan's going to do now is talk about some sort of future-looking things while I start prepping the demo.
Okay, I think we got about 15 minutes left, and we'll go ahead and just push through this and get to the demo. This is the way ahead. This is what we see for the future of the project. We want to stitch multiple roofs together. What we've been talking to you about today is everything composed up in the upper left-hand corner. I guess you'd say just one roof, and that's what we're going to demonstrate to you. But it's much more valuable to put many roofs together and to what we call a roof collector, and then ultimately bring them all the way back to the parent roof, which would be Kanga. Now, it's important to note that our vision is to have each one of these boxes promotable to the next level, kind of like a DC promo. And so you just go in and select and say, hey, you're now a collector, and here's your subordinate roofs. It's kind of what we're hoping to do. These are possibilities. If we can actually pull this off and get you guys involved, and if you want to participate in this, we have the potential of putting together what we call a global honey grid. And a honey grid is essentially just a collection of honey nets. It's a term that we coined a little bit ago. And the idea is that if we do this, then we can have global attack trending. Now, I know there's others out there already doing that, but as Ed has shown you and will show you in our demo, I think we can offer the next level of attack trending, because we can actually get down and tie the packets to the files and actual processes. We hope to have a global zero-day discovery tool, so that as we have these sensors out there, we can use hashes and so forth, and we hope to develop signatures for the attack based on the process tree, and then be able to quickly hash out the normal processes and be left with some suspect processes, and hopefully there'll be some 0 days in there. And then that's pretty much it. Okay, now we're going to move right into the demo. Now, what we've set up for you is a very simple demo. We have 3 VMs. We have an attacker over here, and it's going to go. The connection is going to go straight through the honey wall, again, a layer 2 bridge, and the attacker is going to hit the honey pot. These are the IPs that we have. If you're paying attention, we're going to show you the initial attack from the attacker. He's going to do it the worst of all possible ways. He's going to do it encrypted. So we're just going to demonstrate a brute force login on a SSH daemon we have running on a honeypot. Nothing fancy. But the idea is that we want to be blind. We want to show you that from the network point of view, we're blind from the roof's perspective. We're going to collect everything via CBET. Then once he gets onto the honeypot, he's going to create a rogue directory real quick, move a file in, touch some stuff, and then he's going to SSH back out to presumably one of his other machines, because he needs some more instructions or tools or whatever. And we're going to demonstrate that too, and we're going to show you what we can piece together with Walleye. Okay? Hold it. Okay.
So,
oh yeah. So the first thing you're going to see is that he's on the attacker box right now. It's just a Linux VM. I think it's Fedora or something. And he's going to go ahead and attack into the honeypot, which is 10.0.0.20. He's just going to log in via SSH. You can insert your favorite attack right here. Okay. Now that he's on, he's going to go ahead and create a rogue directory, probably in the dev folder somewhere. He's going to just create a ... directory. He's going to go into that ... directory and go ahead and copy over the password file. And then, as usually the case, he needs instructions that he left somewhere on another machine. So he's going to go ahead and SSH out to that other machine. We're going to go ahead and just SSH back to the box that we attacked from, just to keep it simple. And when he gets to that other machine, he's going to go ahead and cat a large file. Okay, so that's pretty much it for the attack. So we came into the honeypot, created a directory, moved a file in, and then SSH back out. Both of the path ingress and egress was encrypted. So now we're going to go ahead and show you what happens whenever you in the analysis point of view comes into work the next morning. Yeah, just double click on the, there you go. All right, so again, this is the analyst view. You went ahead and logged into Walleye, and go ahead and take it in.
So it'll take a second. I said near real time. It's within an order of a minute that you'll start seeing basically a spike on this chart. So what we want to do is pretend that I came in the morning here and I'm getting about to go grab my coffee. And so what I want to do is I want to hop on the analysis interface and scan to look for any abnormalities. And of course, within the world of honey nets, one thing that's always abnormal, we just got the refresh, is outbound connections. That's always a pretty surefire way to say, I better take a look at this thing because I shouldn't have any outbound connections. So, I'm coming in for my coffee, I see a spike on the chart, and I see an outbound connection. All right, I might want to go look at that. So, okay, we click on the outbound connection. And what we see is we've got an inbound connection from .20 to .30. The initiating host was Linux, and there's a whole bunch of data being transferred. Now, of course, interestingly, there wasn't there's no IDS event, of course. This is, again, the outbound. So I say, well, that's interesting. We shouldn't have had that. Let me take a look at the process tree to see what was the cause of this initiating, of this outbound flow. So we basically take a look at this puppy and we say, well, this looks like a telephone pole, but what we see is SSH. We see SSH coming out of SSHD, okay? Which basically means somebody SSH'd in, got a bash shell, and then turned around and went right back out. So I click on that parent process, which allows us to navigate up and down the tree, as you see. And what happened? Oh. What's this thing doing here? Excuse me for a second here. I can't get to my scroller. Yeah, see, it went away though. See how it went away? Oh, here we go. I figured it out. Okay, so there we go. And so what we see here is basically we now can see we have an SSH. What we've done, we've basically gone to the parent process, and we're looking at the process tree. This is basically, this is a causal sequence of events here. We have a process tree, shows we on SSHD. Here's a SSH we came in on, we started looking at. So looking at this guy, down below here, we see we've got a series of flows. And what we can see is these are all the flows that are related to this process tree. We've automatically pruned that data we had earlier. And as a result of that, we can actually see we've got an inbound connection from .30 to .20. The .20 was the honeypot. So we've, within a couple clicks, already found the inbound flow related to that, that outbound flow. Okay. Now, if we want to basically say, what did the person do on the system, we click on this View Details of the Process button on the far right, and we get to a new view, and this is a process-centric view. What we have is a list of open files that were opened by this specific process, and then also a list of file descriptors we saw read activity on. So with this, we can see which files were touched by a process, and then also what activity. For instance, here, we can see, if we click on Read Details, we are going to get the keystroke activity of the individual once they log into our honeypot, okay? So again, we can see here they created a directory in dot, dot, dot. I don't know how many dots I put in there. They copied the password file over, and then of course, it's a pretty good guess that when they SSH to .30 that it might have been a human because there's a delete in there. That's a pretty good indicator that you're not dealing with a fully automated script. The scripts usually aren't sloppy, right? I am, however. So, okay, great. That's pretty interesting. What about those what about the keystrokes when the person logged into us and they turn around and went outbound? Can we get those? I would guess that we could. So let's see about that. So we're going to go back to that SSH session. Not the SSHD, but the outbound one. We're going to click on that process and we're going to say show details for this puppy. Okay. Now the trick is each process does different reads on different file descriptors, so we kind of have to guess with some of this stuff here, right? So if If I go to FD3 and I click on that and say, is that going to be my keystrokes? Well, no, FD3 for SSH out is going to be the protocol negotiation with the server. Okay, so maybe I want to go a little bit lower here. And what we see in this case is this is actually the keystrokes that we're going to the remote host. They did an LS and then they catted that hacker file, right? Now, interestingly, what's this other inode here? Anybody know what that is? That's the password they used when they were authenticating the remote host. So
Via SSH.
yeah, that's the SSH password. So if somebody breaks into the honeypot, we get not only do we get their data when they come in, but if they then use us as a stepping stone, we're recording all their keystrokes from that point on, no matter how many points they add to that stepping stone. We're getting their passwords, we're getting everything. And no matter how many hosts they keep adding to that, we keep collecting. So that's just a sort of a quick, typical use scenario that describes some of the initial capabilities of the interface. Yeah?
Name of the file was hackers.guide.
Yeah.
Via tab.
So it said,
Yeah.
hacks.
Yep. The reason why that is occurring is we just basically, when we catted that, we probably created a whole lot of data. And as it currently stands right now, this is a UDP export format, the CBEC is, so it's a bit lossy. If you're in an environment where you're worried about that happening, what you probably want to do is put a second NIC on your honeypot and exfiltrate the data over that other link.
One other thing is I think he typed hacks and then hit tab.
Yeah. So we just lost one key.
Yeah. But I think the money shot was the passwords. So again, they came in via encrypted, went out encrypted, so we should be blind from a network point of view, but we were able to pick up all their keystrokes and their passwords subsequently. Okay, so now just flip it back 1 second. We just got a couple minutes here and we'll wrap it up and open up for more questions. So how can you help? And of course, there's many more features to that route. You know, we could use another hour and show you all the other bells and whistles we put in, but we encourage you to go out and download it. So how could you help? You can volunteer. We need more beta testers, badly. You know, as good as our development team is, I'm sure there's bugs in there and we need to get them flushed out. So please, write down this email address, contact us. We'd like to get you involved. There's a honeypots mailing list, and we use that dual purpose. We also use it for honey-nets. So if you want to just subscribe and get up to speed on some of this stuff, we could use some funding to the organization. It's a nonprofit organization. If you're sitting here and you're in a position that you could contribute funding for research and so forth, we have some vehicles in place that we can hook you up with and make that happen. And of course, please buy the books. These are some of our key sponsors, and we'd like to put you up here too. That's all we have. Any questions? Any other questions? Yes, sir. What is the communication between the CBEC and the RU?
Okay, so I didn't go into too much detail on CBEC, but
Just make it brief.
right, it uses UDP where it sends it from the kernel level, generates its own packets, and exports them in a hidden fashion to the RU. The RU passively sniffs them.
And the key thing is that from the attacker's point of view, he's blind to that because the rootkit is keeping him from seeing those packets leave the system. So there's a lot of information out there on CBEC. Please go to the website and get it. Any other questions?
Yeah.
When you start looking at having your collector, your second tier in the architecture, how do you envision handling all the data?
Good question. The question is, once we start to stitch together these routes, how are we going to handle the data flow? What we're thinking about right now is request on demand, or pull. We're going to pull the data on demand.
Right.
Our first thought was we're just going to push it all up the pipe, but that doesn't scale, particularly if one of your sites is on the other side of a satellite or something.
That's why we have a slow path, fast path originally.
Yeah. So,
Aggregate the fast path data or a subset of fast path.
yes.
Yeah, correct.
And then you can also pull the API data on demand. So you can easily go in and say, give me PCAP data from yesterday from 9 to 10, and it'll pull that on demand. And that's kind of where our dream is. And we want to do that via the web connection, just to keep it simple. And so we're probably going to use CGI or something like that. Any other questions? Does CBEC have a Windows port?
Yes, it's the socket tracking and whatnot is currently in development. We were going to hope to debut it here, but our lead developer is up to his ears in gainfully employed type activity. So, we talked about funding. Funding equals time for us. So
Yes.
right now we're low on funding, so we're low on time sometimes.
What OSs are supported by CBEC was the question?
In the Gen 3 world, we've got a 2.6, which is in an early beta, 2.4, and there's some BSDs that are covered as well. And Solaris, I think, will be coming this summer.
Okay.
Okay,
Thank
I'd like
you.
to
Thank
close
you for your
this
time.
session and move some of the more informal questions over to the corner so we can set up for the next session. Thank you.
I'm afraid.